So we start. The quiz is going to cover two lessons, the percent yield in stoichiometry and the forces of attraction. So let's begin with the first lesson. What does percent yield represent? It's the ratio of reactant to product. That's not a percent yield. That's what we call mole ratio. So not the answer. The amount of heat released, the efficiency, how good or successful a reaction is. So yes, this is what a percent yield represents. Okay, next. So the answer is C. Which of the following is typically calculated using stoichiometry? When I do my calculations on the equation and I take whatever is given to me, mass or mole, and I multiply it by the mole ratio, we are finding the theoretical yield, yani the amount of product, the maximum amount of product obtained in a perfect condition. So actual yield is obtained experimentally. It is not calculated. You perform the experiment and you measure the mass of the actual yield. But theoretical yield is what you calculate using stoichiometry. Distinguish between theoretical actual yield and theoretical yield. The actual yield, it's the real mass of product obtained, mass of product obtained in a chemical experiment. After, of course, facing the errors and whatever conditions in an experiment. Okay, so it's always in a laboratory experiment, the mass in reality, and it's always either equal or less than the theoretical yield. That's the actual yield. Now, theoretical theoretical yield is the mass of product obtained from calculations. You do your calculations on the equation using stoichiometry, obtained from calculations using, or I can say from stoichiometric calculations. Okay, from stoichiometric calculations. And I need to mention here, it's the maximum amount of product that can be obtained. The maximum amount of product that can be obtained. So the reaction, the calculations will give you an idea what to expect. Now, define any, is it clear? If there are questions, please stop me. Define percent yield and explain what it measures in a chemical reaction. So a percent yield represents it gives an idea to the chemists to evaluate the success of a reaction. So it shows the efficiency. You might not like the word efficiency. It shows how much successful a reaction was. So you perform your reaction in the lab and you measure the percent yield to see what was the expectations and what you obtained in reality. So we always calculate the percent yield so that we make improvements or repeat the experiment to see if we can make it better. So how successful the reaction, which is not a common reason actual yield is less than the theoretical yield. So actual yield is either equal or less than the theoretical yield. Now, why? because sometimes there will be side reactions going on or some impurities that will prevent us from obtaining a high amount of actual yield, all or some errors in purification, or we lose a product while doing the purification. Okay, now this question is telling you which is not a reason. Excess of a catalyst, excess catalyst. Catalyst is a substance that speeds up a reaction. It has nothing to do with the amount of product obtained. So catalyst, it's like an enzyme. It makes the reaction goes faster. So it has nothing to do with the results of the reaction. So that's not a reason. Now another question. Note that the formula of percent yield will be given to you in the quiz. So it's the actual yield over theoretical yield. Now, the students, they always, many of them forget to multiply by 100. So please be careful to this. So a reaction has a theoretical yield of 50. So here I'm going to write 50, but produces 40, but produces 40. That's the reality. We were expecting 50, but we got 40. So what is the percent yield? So the percent yield is 40 over 50. So that's an 80%. So this is a very good result. 80% successful. Now moving on. In a reaction, so in a reaction, we have 5 gram of product was expected. Was expected. Yani I'm explaining here that we did our stoichiometric calculations and the maximum amount that we should obtain is 5 gram. So 5 gram is the theoretical yield, but only 3.75 was recovered. So that's the reality. That's what happened in real. That's the actual yield. These questions are just direct application to the formula of percent yield. So the percent yield is the actual over the theoretical times 100. So the answer is going to be 75%. Also, this is a successful result. Which yield value most accurately reflects the reaction's efficiency? Efficiency means how good the reaction is, and that is the calculated percent yield. Now, moving on, predict which of the following reactions is better, more efficient, more successful. So here you can calculate the percent yield of every reaction in order to compare percent yield of A and percent yield of equation of or of results of B. So it's always actual over theoretical multiplied by 100. Actual over theoretical multiplied by 100. So the efficiency of this one is 75%. Now for the second one, actual over theoretical multiplied by 100. So that is 60%. So which one is more efficient? Reaction A is more efficient. So from the calculated results. Next. Now, this is just fill in the blank or quick questions to make sure that the concept is clear. So, which of these is not a reason for percent yield to be less than theoretical yield? Oh, I forgot to put the choices. So, well, the reason for not a percent yield, for an actual yield to be less than the theoretical yield. So side reactions, this is the same repeated questions. Side reactions is a reason. So let's just change the question and say which one is a reason for actual yield to be less than the theoretical yield. Or impurities or reaction did not was not completed, was not completed, it didn't finish. Lost of product during purifications, or what I call experimental errors. Now, the amount of product actually produced by a chemical reaction is called, so you do the chemical reaction, whatever product you obtained is what we call the yield, the actual yield. Yield يعني product. The is the maximum amount of product. It's the maximum amount of product that can be produced from a given reaction. That's a theoretical yield. And I'm highlighting the word maximum because theoretical yield, that's the maximum I can get. You do your calculations if the reaction is error-free, so that's the maximum that you can get. The ratio of to the expressed as percent is called, okay, what I know, this is percent yield. And they are here asking you for the formula. Percent yield is actual yield over theoretical yield. So dividing it, that is called ratio. So the ratio of the actual yield to the theoretical yield is what we call percent yield. A chemical reaction rarely produces the product. So I assume here that we rarely get the exact amount of theoretical yield. Actually, there is no perfect reaction, so we can never get the correct amount. And if, for example, I'm expecting 9 grams of product, I can get 7 grams. Amazing. If I get 8.9, which is impossible because there is no reaction that can give you this high efficiency. So that's why we're saying rarely. So a chemical reaction rarely produces the exact or the theoretical yield of the product. Okay, so here we're talking about the exact amount or the full expected amount if you want. So let me just call it the theoretical yield of the product. So again, what's relationship is used to determine the theoretical, the percent yield, actual yield over theoretical yield times 100 is called percent yield. Just a formula, do not worry about it. It will be given. Now, let's begin the calculations. That's the most important part. So, when you read a question, always in the question, there are two numbers given. You need to identify which one is a mass of a reactant that you are going to use to find the theoretical yield and which one is the actual yield. And again, I'm going to give you the way to do it. Ethanol, so that's ethanol, is produced. So this is the product. Ethanol is produced from the fermentation of sucrose. So this is sucrose. This is sucrose. Now, determine the theoretical yield and the percent yield of ethanol if, okay, let's hear, 684 gram of sucrose. This is the mass of sucrose, and that's sucrose, and it's over here. So this is a reactant mass that I'm going to use and undergoes fermentation, and you get 300, oops, here, So you get 349 gram of ethanol, and ethanol is this one. I'm highlighting it in pink. So that's the actual yield. Here, usually in the question, they give you the molar masses. So let's do the solving. So first of all, determine the theoretical yield. So theoretical yield, it means the mass of C2H5OH obtained expected theoretical yield. We start with the mass of the reactant, 684. You're gonna divide it by the molar mass of C12H22O11. And then you're gonna multiply it by the mole ratio. What you want, C2H5OH over what you have, 1 mole of C12H22O11. Keep in mind, always in the mole ratio, you put the number of the product over the reactant. And then finally, after you're done with this step, you are going to multiply it by the molar mass of the product you're looking at, C2H5OH. So now let's substitute with the numbers. So, of course, in the periodic table, it will be given, and you will be calculating the molar mass, or maybe it will be given in the question. So the molar mass, I'm just going to do it now quickly, of sucrose is 12 times 12 plus. And so the molar mass, I just found it. I used the periodic table, 342 times 4 over 1 times the molar mass of this one is 46 gram per mole. So the final answer would be 368 gram. That's what I am expecting, theoretical yield of C2H5OH. Is it clear? Please, if there are questions, let me know. Now, okay, we need to find the percent yield. Percent yield is the actual over theoretical. Always, you will know actual is less. You're not going to get over 100% result times 100. So it is 349 over 368 times 100. Whoa, that's a 94.8%. Moving on. So here's a balanced equation. It says, determine the theoretical yield and the percent yield if, again, let's use this same technique. PBO, it says, wait 1 second, let's read. The percent yield of PBO. PBO is a product. And then it is saying, if 200 grams of PBS. So be careful, this 200 gram for this one. So that's a reactant. It means that's the given mass. And the experimental procedures showed, yani we did it in the lab, showed that only 150 grams were collected. So that is the theoretical, the actual yield. So 150 gram of PBO, and PBO is in the product. So that makes it actual yield. So let's begin. Again, the theoretical yield, mass of PBO, theoretical yield, is equal to the given mass of reactant over the molar mass. I'm going to get this from the periodic table. Molar mass of PBS multiplied by the mole ratio product over reactant. 2 over 2 multiplied by the molar mass of PbO. Now, using the periodic table, just a minute, I'm going to get the molar mass of lead. So it is 207 plus 32. So here the number is 239. Okay. And for this one, it's 223. So the final answer, it would be 186.6 grams. That's the theoretical yield. So the percent yield, we got 150. We were supposed to get 186. So 150 over 186 times 100. So that's an 80.6%. Now, moving on. So the last question that I'll solve, and then I'll move to the intermolecular forces. Upon heating, calcium carbonate decomposes into calcium oxide. So they're telling me that is the product. Determine the theoretical yield if the theoretical yield of CO2. So they are interested in the yield of CO2. If 235 grams of CaCO3 is heated, 200 grams of this is given. So this question is done in steps because as you can see here they've given us the actual yield. So we start with the mass of the given reactant. Again, the mass of the given will be divided by the molar mass of the reactant, and the molar mass of calcium carbonate is 100. So multiplied by 1 over 1 and multiplied by the molar mass of the theoretical yield we are getting. So it's carbon plus 2 oxygen. So finally, the answer is 103.4 gram. That's the highest amount that we can get. Now, what is the percent yield if 97.5 is collected? See, it's always less. We were supposed to get 100. We got 97.5. So 97.5 over the theoretical yield times 100. That's a 94.3%. One last question. So methanol wood alcohol is produced when carbon monoxide reacts with hydrogen gas. So carbon monoxide reacts with hydrogen gas. These are the reactants. Now, it's saying that 8.5 grams of carbon monoxide, that's a given reactant, react with excess hydrogen, and 8.52 grams of methanol is obtained. So that's the actual yield. So here, the actual yield. So the question that they break it to you into parts. So how many moles of carbon monoxide were reacted? So first, in the first step, we are finding the mole, just like the previous question. So here they're telling you how much is the mole. So 8.50 grams, because we're using, to find the mole, we do mass over molar mass. So 8.50 divided by carbon monoxide. That's a 12 and 16. That's a 28 gram per mole. So 8.5. The mole would be 100 mole. Now, after this step, we calculate whatever mole we get by the mole ratio. And the mole ratio here is 1/1. So they are asking what's the theoretical yield of methanol in mole. Yani stop here like the previous question. So 0.304 times 1/1. That's so here it was mole of CO. Now it is mole of CH3OH. Then we multiply to get the mass of this theoretical yield. So the mass of the theoretical yield is 0.04 times the molar mass of this one, which is 12 and hydrogens and all the oxygen, 32. So the final answer is 9.728 gram. That's the theoretical yield. And the actual yield is this one. Here's the actual yield. So 8.52 over 9.728 times 100. So 87.58%. Are there questions for the first part before I move on to the forces of attraction? Okay. Now, intramolecular forces and intermolecular forces. So, intramolecular forces are the forces of attraction that occurs between inside the compound itself. So, for example, within the molecule. So, intramolecular forces, forces of attraction within a molecule. So, if I have H2O, these are the intramolecular forces. Yani, for example, between or combining the atoms together are the forces within a molecule. So holding atoms together. Whereas intermolecular forces are the forces of attraction between, not within, between the molecules. So if I have a molecule of H2O and another neighboring molecule of H2O and on and on and on, the forces of attraction would be the intermolecular forces that we're talking about are the one that I am doing in dashed lines. These are the forces of attraction. So usually the forces of attraction, the intermolecular forces, are abbreviated as IMF. They're weaker than the intramolecular forces. Okay? I would like also to mention that the intermolecular forces we're doing are London dispersion forces, dipole, and hydrogen bonds. Whereas the intramolecular forces, the ionic bond, the metallic bond, the covalent bond. So please memorize these type of bonds. So let's move on. Which of the following is an intra, inside the compound? So that's an intermolecular forces over here, intermolecular force over here, intermolecular force over here. So the answer is covalent. Now, which bond type involves free moving electrons in a sea of electrons, or free delocalized electrons in a sea of electrons, and that is the metallic. So you need to remember the definitions, and I'm gonna do it over here. The covalent, you have non-metals sharing their electrons, so there are no free moving electrons. In the ionic, you have a metal transferring electron to a non-metal. So there is no free moving electron. The only one where there are free moving electron, sorry, sorry, is the metallic, where you have positive ions. These were the metals that lost electrons. So a metal, after losing electron, becomes a positive ion. So in the metallic, we have positive ions surrounded by a sea of delocalized. Delocalized means moving, mobile, تحرك, moving electrons. So please remember, we can also say negative electrons if you want. Okay, but not negative ions. We don't say delocalized ions. It's delocalized electrons. Now, let's do our comparison again in this table between the three types of intramolecular forces. So, in ionic, we studied the crystal lattice. In the covalent, we call it molecule. In the metallic, it looks like the ionic, but it's surrounded by a sea of delocalized electrons. So it's a lattice surrounded by mobile or moving negative electrons. Okay, so atoms involved only metals. Here, only non-metals. Here, both of them, metals and non-metal. The strong, this is the strongest. This is in between. And wait. No, this is less strong, like in between. And this is the weakest, but it's not weak. It is strong, but it's weaker than covalent ionic metallic. Weakest among the forces. But itself, it is strong. So do not get confused and think that covalent are weak. They are strong, but comparing them to ionic, covalent, and metallic, they're weak. Okay, I'm just going to write just weak. In terms of properties, always remember the properties. Low boiling point and melting point. Here, high boiling point and melting point. Here, non-conductors, because this is important, but the ionic, they conduct electricity only if dissolved in water or molten. That's the most important properties that you need to know about ionic and covalent. Metallic, you can list any property that you know for metals: conductor, malleable, ductile, solid, because all, etc. So all the metals are solid. Now, which of the following exhibit hydrogen bonding? Hydrogen bonding is an intermolecular force. I'm going to repeat this. This intermolecular force is only present in some, or let's say in specific polar covalent compounds. Specific polar covalent compounds. In the strongly covalent, like very, very, very covalent, very polar compounds. So, and who are the very strong covalent compounds? The very strong covalent polar compounds are the one having bond between H and N. I mentioned it in class. No, H and O, H and F. Any polar covalent compound that you see in its formula H and N or with O or with F, then this compound can do hydrogen bonding. Now, this one only will do London dispersion forces. This is not polar even. And this one, it becomes not polar. The bonds are polar, but they cancel each other. So we don't worry about this. This is non-polar as well. So this is H and N. That's the one that will exhibit London dispersion forces, dipole-dipole, and hydrogen bonding. Now, what best describes a temporary dipole? A temporary dipole, it means it's a dipole that will end, will stop. It's not permanent. So, so the temporary dipole will be, let's see the choices. So it results, it's caused by permanent charge. No, that's a permanent dipole. Results from instantaneous electron movement. That's the definition of London dispersion forces. So there will be electrons in the atom moving around, and these electrons, if they come on a side, like for some instant, this side becomes negatively charged and the other side will become positively charged, and at that point they might have London dispersion forces with another neighboring molecule. Definitely not in the polar molecule. Moving on, compare and give examples of temporary and permanent dipoles. Temporary, you can find them in all kind of molecules, in polar, in non-polar, in atoms. So these are observed in for London dispersion forces, whereas temporary dipoles are observed in dipole forces. These are stronger and permanent. These are weaker and result from the movement or the instantaneous movement of electrons in atoms, molecules, or compounds. Whereas the permanent dipole are stronger dipoles resulting from the unequal sharing of electrons between atoms. Yani what I'm saying here, in polar molecules only. In polar molecules only. Let me give an example here. For the weaker, for when you are giving example for instantaneous dipoles, do not give examples of the one. Yani, I know I said in class that these are all the kind of molecules that you have, but because here we are doing the differentiation between both of them, you cannot just tell me H2O. H2O will have, of course, London dispersion forces, but H2O also have dipole-dipole, so please don't use this example. Put here examples of compounds that only will have instantaneous dipole. And that is, for example, any atom, argon, helium, neon, any just an atom alone. Or any non-polar molecule like H2, O2, N2, CH4, Cl2, etc. Do not put examples when you are talking about temporary dipoles. Do not put examples that also have permanent dipoles. Okay? Now, another example of permanent dipoles, HCl. I mentioned in class, look at the periodic table. It's from both sides of the periodic table. You will then notice that there's a big difference in the electronegativity. So this compound is polar. HF, H2O. Memorize these well-known compounds. NH3, H2S. So HCl, HF, H2O, and H3, HBr, HI. So whatever compounds that you know, but do not give me a compound that does not exist. So please be careful to the examples that you are given and keep few in mind. What best explains dispersion means London dispersion forces. So why they are equal? They definitely don't go between charged ions. That's for ionic compounds. They involve no real dipoles. We don't say no real dipoles. We say like partial charges. So instantaneous dipoles are real dipoles. So you cannot just say no real dipoles. It's wrong. Covalent bonding, where this is involved in intramolecular forces. They are caused by temporary, not permanent, instantaneous dipoles for low polarity, or what they mean for non-polar compounds. Now, strongest intermolecular forces. In order to answer a question like this, you need to list in your head, in your mind, what are the intermolecular forces of each one. So, I'm going to show you these atoms on the periodic table. That's a C and that's a H. And I mentioned that whenever there's a bond between C and H, it's non-polar. So this compound will only have London dispersion forces. And all compounds will have London dispersion forces whatsoever. However, some compounds will have more. Now, let's see. Is there anything else? No. For the H2O, H and O, this is polar. So this will have also dipole-dipole interaction. CO2, this is this one is a non-polar overall molecule, but it does have some dipole-dipole. It confuses the students. So I'm just gonna say dipole-dipole, but these dipole-dipole are cancelled due to the structure of CO, so they cancel each other. So that's why we keep on saying that CO2 is non-polar. So it's okay, just mention dipole-dipole. Just keep that in mind. Okay, but they're weak because they cancel each other. And N2 only London dispersion forces because it is over here the N. However, this compound particularly is polar, and the polarity is between O and H. And I said, remember, NOF. So there's O and H here. So it also has hydrogen bond. So let's look in here. The strongest intermolecular forces will be for the one having all kind of intermolecular forces. So that's come first. This comes second. And then here, A and D. If I want to say which one is stronger, I need to find the molar mass or the number of electrons. The molar mass of this one is 16 gram per mole, and here is 28. So if I want to rank them from stronger to weaker, it would be like this. So again, rank the following in increasing strength. So before you do any ranking, you just mention the force, the intermolecular forces present in each one. London dispersion forces always. Now, C and H bond are always non-polar. So finished for CH4. N, HN in the periodic table or HCl, both are polar. So both of them will have dipole, dipole. However, this has H and N, the NOF that I told you about. So this one will also have hydrogen bond. So it's very clear now. The weakest CH4, next HCl, next NH3. Now the justification is this, because you can just mention it in words that CH4 only has London dispersion forces, whereas HCl is a polar molecule. It's a polar molecule. You have to mention that this is polar and has London and dipole forces. The only one that is very polar is NH3 and has all kind of intermolecular forces. So that's why it is stronger. Now, consider the following. Which of the following is true about magnesium? Magnesium is a metal, so it is solid, it conducts electricity, it is having positive cations surrounded by negative electrons, a sea of delocalized electrons. So the first two only. Which of the following correctly list the substances in decreasing from high to low forces of intra? So this one, so here CO2 covalent, Mg metallic, and CAF is a metal and a non-metal ionic. So that's the highest, then second and third. So A. Which of the following is true about hydrogen bonding? Hydrogen bonding is okay, I was about to circle this one. It's wrong. It's not an intra. It's an the strongest intermolecular force. So that's wrong. It occurs between HF. No, yes, between molecules of HF. And it's a very strong dipole-dipole force. Correct. It's a category of dipole-dipole that it is very strong. Moving on. Look at this compound. Intra, in the molecule itself, intramolecular force, whereas this one, intermolecular force, same as well the Z and the W. So intermolecular force, Y, Z, and W. X is an intramolecular force in a compound of H2O, which is covalent. So that's a covalent bond. So intra-covalent bond. Metallic metallic bonding is an attraction, again, between positive metals. You can call them positive cations or positive ions. So it can be said cations are the positive ions. So it's the attraction between positive ions surrounded by a sea of delocalized electrons, by free moving mobile electrons. So it's always in metals. That's covalent, that's ionic again, this one. Anion, no, it's not anion and delocalized electrons, it's metal cation and delocalized electron. Which of the following is not an intra? Intra are ionic, metallic, covalent. So London dispersion forces is not an intramolecular force. HCl, a sample of HCl. Before you continue, ask yourself, what are the intermolecular forces? London dispersion forces for sure. Now go to the periodic table. That's hydrogen and Cl is here. They're too far from each other, then definitely this is polar and it will have dipole-dipole. Is it NOF? Is it HN or HO or HF? No, it's HCl. So that's it. London dispersion forces and dipole-dipole. So they're looking about the forces between the molecule, not inside the molecule, to take number one. So 2 and 3. Moving on. Consider the following diagram that represents the forces of attraction between molecules. You have to read carefully if the question says in the molecule or between the molecules. So we're talking about intermolecular forces, and they are the dotted, not the solid lines. Okay, compare and contrast the two different forces in the table below. So, okay. So let's first look at this one. So here, one second. The first one is a dipole-dipole interaction. It shows. Let me see. I think these are the same molecule. So, and it's just one. So it's a bit confusing, this one. So I think that W, and I don't think, I'm sure that this is London dispersion forces, okay? Because here I know from the molecule that this is HCl maybe, or HBr or HF. So here it has dipole-dipole interactions. So London dispersion forces are weaker and the dipole-dipole are stronger. The London dispersion forces, okay, let me write it here, they exhibit temporary dipoles, where here permanent dipoles, and we call them dipole-dipole. So it's the same question repeated. Which molecule possesses stronger force between its molecule? Well, of course, the H, because H molecules will have London dispersion forces and dipole-dipole since they are polar. By just mentioning what are the intermolecular forces in a compound, you are ranking it, you are ordering it, whether it's strong or weak. Plus, here we're talking about permanent dipoles. Here we're talking about temporary. Plus, it has permanent dipoles that are stronger than the temporary ones. Moving on. You will see next week that the intermolecular forces affect the boiling point. The larger the boiling point, the more forces it has. So when I look at this one, this is the largest number, it's plus 20, this is minus, this is so in the negative. So that's weakest. Now, let's just think about the forces. Here they want the intramolecular force and the intermolecular force. So without thinking, all the compounds will have London dispersion forces. Okay. Now, only the polar ones will have dipole-dipole. Now, this is HCl, polar, This is NH3, very polar, NOF, and this is very polar. So this one will have dipole, dipole, finish. This one will have dipole, dipole. This is NOF and hydrogen bond, dipole, dipole, and hydrogen bonds. Now, all the examples given to me are all between non metals if I look at the periodic table. So all of them are covalent. They have covalent intermolecular forces. Now, based on your answer in part A, YHF, since it has same intermolecular forces like NH3, YHF is still stronger. Okay, so um, the reason, if I look at the periodic table, that's HN, and that's there's O and there's F, that's HF. F is the most, we studied that in term 1 is the most electronegative element in the periodic table. So if I want to compare polarity, this is very polar, but this is very, very, very the highest polarity ever. So that's why the hydrogen bonds here are stronger than the hydrogen bonds there. They're both strong, but stronger because F is more electronegative than N. So it makes it very polar. So when you are writing, please mention that this is extremely polar. Now, I'm moving faster because I have another session. So one line, okay, so we're gonna match. So let's see. Hydrogen bond, dipole, dipole, London dispersion forces are the intermolecular forces, whereas ionic, covalent, and metallic are the intra. So these attractive forces are found between HF molecules. So intermolecular forces. And since they mentioned HF and I know NOF, then definitely we're talking about hydrogen bond. Now, since HF has hydrogen bonds, so definitely it's going to have London dispersion and dipole, dipole. These forces are formed by instantaneous that goes for the London dispersion forces. London dispersion forces. If they mention permanent, I'm going to take only dipole forces and hydrogen bonding. They are the strongest intermolecular forces. We're talking about hydrogen bonds. The weakest among intracovalent and result from attractions between cations and C of delocalized electrons, metallic bond. Now, moving on, use your knowledge about intermolecular forces and intra. In NH3, London dispersion forces, dipole, dipole, and this has no hydrogen bond. So here we have the three kind of intermolecular forces. So I'm going to write this here. And for intramolecular forces, any polar or non-polar compound means is a covalent. Will have covalent bonds. Now we're almost done here. So arrange in the order of their boiling point. You have to keep in mind that the weaker, the less intermolecular forces it has, the lower boiling point. So let's first look at the intermolecular forces. London dispersion forces, London dispersion forces, London. Okay, this is not going to fit. So this one, LDF, this is an ionic compound. Keep that in mind. This is LDF, and this is a metallic compound. This is non-polar molecule, covalent. This one, LDF, it's polar, and north hydrogen bond because it's covalent. And this one, London dispersion forces and dipole-dipole. So the picture is clear. The more bonds it has, the higher the boiling point. Okay? Now, we always exclude the ionic bond because the ionic bond is the highest ever. So, NaCl is the last one. Okay? And then what comes after is a metallic covalent metallic compound. And now we start ranking the weaker one, the one that has covalent bond, and we look at their intermolecular forces to rank them. So HF, HCl, and H2. So that's the increasing boiling point. Here comes the lowest, and here comes the highest boiling point. Finally, the last question. This is nonpolar. Always think about nonpolar covalent. This is ionic, metal, non-metal. This is metallic. So, okay. The melting and boiling point, we're talking about properties of ionic is always high, and of metallic also is high. The only compounds that have low melting and boiling point are the covalent, non-conductor, and those are conductor only in aqueous solutions or if molten, and always here conductors. Now the last question, which type of intermolecular forces are present in Z, the metallic bond? So it's a metallic bonding, be careful, intra, metallic bonding resulting from moving free electrons between positive cations. Okay, so which species these present at room temperature? Of course, metals are solid. And that's it. I'm done with the revision session. I'm going to stop the recording. I will post this on my YouTube channel. You can watch it and prepare for your quiz. Thank you for watching.